This is a short lecture. I think there's only 18 slides where I'm going to step you through step by step the algorithm of rigorous coupled wave analysis. So here is a summary of the algorithm. And step 0, I call it a step 0 because this is no part of the program. This is what we do before we even sit down at the computer. We decide what type of device we want to model. What are its dimensions? What are its material properties? What type of source is hitting it? What type of information do we want to get from the problem? So all this needs to be settled before we even sit down at the computer and do something. Then we enter the code proper for rigorous coupled wave analysis. And we will initialize the MATLAB environment. We will define all of the different material properties, dimensions, source conditions, etc. So all the hard-coded numbers will appear right up front in the code, and then everything else in the code will not be hard-coded. The second step that I like to do is build the device on the grid, and these are very high-resolution grids. Remember back when we were talking about Fourier space, we were constructing the convolution matrices, and we were Fourier transforming unit cells, and we looked at how many points on the grids we needed so that we got an accurate calculation of the Fourier coefficient. So we're building these devices on very, very high resolution grids, nothing like what we're doing for finite differences. So we need grids that have at least several hundred points along each axis. Once we've built the device on these grids, we build the layers. So we just have a series of 2D grids where we're describing the cross sections. We'll see more of that in this lecture. Step 3 is pretty simple. Once we have this convmat function that calculates the convolution matrices, we just go layer by layer and construct the convolution matrices. Next, we compute our wave vector expansion. Remember, we're representing the field in each layer as this expansion of plane waves, all at different angles. Plane waves, and in fact, a lot of these evanescent fields as well. Only the lower order, few of your spatial harmonics are actually propagating plane waves, but we can still think of it as a plane wave expansion. So we calculate all that, all the wave vector components, x, y, and z's. Then, because of the way we're doing our scattering matrices, we'll calculate the eigenmodes of free space. And those are used for our formulation of scattering matrices, really nothing else. We will initialize the global scattering matrix. And remember, this is the nothing matrix, if you will. So it's 100% transmission, 0% reflection. Then the main loop of the program, where we step through each layer, just like we did for the transfer matrix method. We're going layer by layer and calculating a scattering matrix for each, and then using a star product to update the global scattering matrix. So for each layer, we will construct our P and Q. Then we will calculate all the eigenmodes that exist in that layer. Then we construct the scattering matrix for that layer, and then we update the global scattering matrix. And we repeat this for every layer in our stack up. After we're done the main loop, just like we did for the transfer matrix method, we will calculate the reflection side scattering matrix. Step 9, we'll calculate the transmission side scattering matrix. Then based on these two scattering matrices that will connect our current global scattering matrix to the outside world, we'll update the global scattering matrix with these, and now we've connected our device to the outside world. Now we're ready to calculate the reflected and transmitted fields. And this step will also include calculating the longitudinal components of the fields. Once we know all of the fields on the reflected and transmitted sides, then we'll calculate the diffraction efficiencies of each of the spatial harmonics. And once we're done that, then we can add up all of the reflected spatial harmonics to get total reflectance, all of the transmitted spatial harmonics to get overall transmittance, and then the very last step, we'll add the reflectance and transmittance together and make sure we get all of our energy back. And as long as we haven't included any loss or gain, we should get our energy back and have 100% conservation. So here we go. This is the step-by-step, talk you through each step of the rigorous coupled wave analysis algorithm. So for this example, we have a crossed grading, if you will. It's a square array, maybe it's even a rectangular array of triangles. And so to describe this in rigorous coupled wave analysis, we see there's actually 4 regions. We have a semi-infinite reflection region. We have a semi-infinite transmission region, but the device itself is composed of two layers. We have one layer that has some kind of triangle function, so there's two different materials here. And then this third layer is a homogeneous layer. And we need to put dimensions and stuff to this next. So here are all the dimensions, and we can see that it is a slightly rectangular unit cell. It has a width of 1.75 centimeters in the x direction and 1.5 centimeters in the y direction. Here are the material properties in the reflection region, material properties in the transmission region, and then the permeability and permittivity in the diffraction grating region. Here are our thicknesses of the two different layers. And here is W, which is a parameter of the triangle. It's the width of one side of the triangle. So the triangle layer, if we're looking at a top-down view, would look something like this. So here's how everything's defined, and here's all of the numbers. So all the numbers in the upper left here should appear at the very, very top of your code in step 1, which is next. So the last two slides, this is all of the information we have to collect, all the work we have to do before we even sit down to code it. Once we're ready to sit down and code it, now step 1 is to initialize the program. So we initialize MATLAB, we define any units. Maybe we want things in microns, maybe we want things in centimeters or meters. Once we've done that, we're in a position to define all of the different constants that we'll need. Maybe, depending what we're doing, we'll need the speed of light, free space permeability, free space permittivity, free space impedance, etc. We may even want to open a figure window if we're going to plot to that. Then, probably most important, we need to define what it is we're going to simulate. So everything about the source that we need, the wavelength or frequency that we want to illuminate our device with. We have theta and phi, which is the azimuthal and elevation angles of our source. We have a polarization vector. Maybe it's linearly polarized, circularly polarized, or something else. So we need everything about the source. Then the device, and this comes from the last slide, but all of the dimensions that we'll need, all the different material properties. If there's anything else, maybe there's information in how the layers are stacked, and we can play weird games with the scattering matrices to more efficiently describe very complex structures. Then we also have the rigorous coupled wave analysis specific parameters. What's the size of our real space grid? This is the high resolution grid where we build our layer cross sections in, and we will FFT those. So how big do those need to be? How many spatial harmonics are we using in rigorous coupled wave analysis? So anything else that's RCWA algorithm specific, we need to define here as well. So that's step 1. Think of this as the dashboard to the program. All the hard-coded numbers go here. We don't perform any work here or calculations. That comes later. Then after step 1, no more hard-coded numbers. Everything is relative to the numbers here. Step 2. We know everything about the device now. What we have to do is go in and build the layers on these high-resolution grids. So unlike finite difference frequency domain, where we think we resolve this longitudinal direction with many, many cells, remember this longitudinal direction, the up and down direction is analytical. So we don't need to store that in any type of grid. So really all we need to store are a picture of the cross-section of each layer in the device. And in this case, we only have 2 layers, and regardless of their thicknesses, we see we have these 2 cross-sections. Well, we're really putting these on grids, so at some level we're making some kind of staircase approximation. We're probably using something like 512 by 512 points, so the staircase approximation is not very severe here, and will get accurate Fourier coefficients. But the point is, these are very large grids. It's a very high resolution grid, but we don't have anything in the z direction. We're just describing the cross sections of all of the unique layers in our device. And in this case, it's only 2. Once we have those, we'll set up a loop, and we'll go through all of the layers, and we'll construct our convolution matrices for those layers. After we've done that, we can, if we want to, actually throw out the information on the high resolution grids. We can delete those from memory, all rigorous coupled wave analysis needs are these convolution matrices. A rule of thumb is we need about 10 spatial harmonics for every wavelength wide the device is. So if in the x direction, if it's 1 wavelength wide, we'd probably start off using 9 or 11 spatial harmonics in each direction. And I'm giving an odd number because we like them to be symmetric. We have the 0 order mode, plus and minus 1, plus and minus 2. But very often we can get away with a slightly smaller number there. And so the answer is, if you're asking the question, how many do we need? This rule of thumb gets you started, but we always look for convergence. You'll try it with a certain number of harmonics, you'll increase the number of harmonics, and you'll see if the answer changes much. At some point, as you're increasing harmonics, the answer does not change much anymore, and we'll say that the algorithm has converged. So that's the rigorous way to test if you have sufficient number of harmonics. Now we're ready to calculate our wave vector expansion. So we'll have two 1D arrays, M and N. So for example, if we have 11 spatial harmonics in the x direction, M would go from -5 to +5, passing through 0. So we'll come up with a 1D array describing the x components and another 1D array describing the y components of our spatial harmonics. Given those, we will calculate the longitudinal components in the reflection and transmission regions, and we use the dispersion relations to do that. And we'll also notice we take the complex conjugate of that, and that's to enforce the sign convention that we use. Remember, that was e to the minus jkz that we've adopted for this. So we'll take the complex conjugate, and that sorts out any signs on the imaginary component. Once we have all of these lists of the components of our wave vectors for all the spatial harmonics, we will form our diagonal K matrices, just like we talked about in previous lectures. So we might want to diagonalize these this way, and don't forget to divide by K naught so that this big square matrix here is normalized. And we might choose to divide by K naught here, or we might choose to divide by K naught when we're calculating these equations up here. Either way works, as long as this Kx square matrix comes out being normalized. Next, to set ourselves up to calculate our scattering matrices, we need to calculate the eigenmodes of free space, because those parameters are used when we calculate the scattering parameter terms. So in free space, our P and Q is the same thing. We calculate it this way. Omega squared is just P times Q. And then we can calculate the eigenvectors and eigenvalues of omega squared. So that comes out being W naught lambda. Then we can calculate the eigenvectors for the magnetic fields in free space. Now we just store those parameters to the side, and we'll reuse those as we calculate our scattering matrices for each of the layers. Step 6, we initialize our global scattering matrix. So we're initializing a nothing matrix. It's this infinitely thin slice of absolutely nothing. So what does nothing do? Well, in terms of reflection, it doesn't reflect at all. So this term is all zeros. In terms of transmission, it has to be 100% transmission, but also not affect the phase. So this just becomes the identity matrix. Transmission in the forward direction is the same thing, and reflection in the backward direction also we do not reflect. So in fact, the scattering matrix we initialize looks like this, and a pitfall that a lot of folks make is they initialize this whole matrix as the identity matrix, and in fact it's not. If it was the identity matrix, we would see the two I terms along this diagonal and zeros here, but we don't see that. So this is not exactly an identity matrix. So I would call this the nothing scattering matrix. So now we enter the main loop. And this is where eventually we will calculate the global scattering matrix of just all the layers that sometimes we call the device scattering matrix. So for each layer, we will calculate P and Q, and then build an omega squared for the layer. Then we'll calculate the eigenmodes with the MATLAB function eig, and out comes all the eigenvectors and eigenvalues. We'll calculate the eigenvectors of the magnetic fields. Now we have all the parameters we need to calculate the scattering matrix for the ith layer. And since ours are symmetric, we really only have to calculate S11 and S12. because S21 and S22 are the same as S12 and S11. So we calculate just like we did for the transfer matrix method. We calculate a scattering matrix for the ith layer, and then we update our global scattering matrix using the star product with that ith layer. And we repeat this over each layer. So each layer we calculate the parameters, calculate the eigenmodes, calculate the scattering matrix, update the global. Go to the next layer, calculate the parameters, calculate the eigenmodes, scattering matrix, update the global. And we just repeat through all of our layers. At the end of that, we have a scattering matrix which describes scattering through our entire stack of layers. However, whatever that device is, whatever that structure is now surrounded by free space, and that may not be the case. So what we need to do now is calculate the reflection side and transmission side connection scattering matrices. So step 8, we're calculating the reflection side scattering matrix. So really just like what we did inside the main loop, we calculate the parameters for the layer, P and Q and omega squared. An important thing here is in the reflection region and transmission region, we have homogeneous materials. So we don't have to calculate convolution matrices. This mu and epsilon are just scalar constants. And in fact, it tends to become numerically less stable if we just go ahead and blindly construct convolution matrices with homogeneous layers. So it's much more numerically stable just to calculate these directly this way. And it's also faster. But anyway, we calculate PQ and omega squared. Then we calculate the eigenmodes in the reflection region, both for the electric fields and the magnetic fields. Then we calculate the reflection side connection scattering matrix. And these are the same equations we use for transfer matrix method. Absolutely no change here. Other than that, we have larger matrices, but the equations are the same. Exact same story for the transmission side. We'll calculate P, Q, omega squared. We'll calculate the eigenmodes, and then we'll calculate the transmission side scattering matrix. Then to finalize all this, we have to put it all together, and we calculate our global scattering matrix by calculating the global scattering matrix we constructed so far and doing a star product with the reflection and transmission side scattering matrices. So we'd write it symbolically this way, but actually in the MATLAB code we'll perform this in 2 steps. So S global is S ref star product, the global scattering matrix that came out of our main loop, and then do it again. S global equals S global star, the transmission side reflection scattering matrix. So it'd be 2 lines of code in MATLAB to do that. So now we have the global scattering matrix. Now it's time to figure out what the fields are on the reflected and transmitted sides. So first step is to calculate this delta vector. Remember, this is all zeros except the 1 usually in the position of the 0 order harmonic, because that's our source field coming in as the 0 order. Given that, we can calculate what the source field looks like. It's the x component of the polarization vector times this delta column vector. And then for the second component, it's the py component, the y component of the polarization vector times this delta vector again. So what we have is a column vector of 2 column vectors here now. The px and py are 2 scalar numbers. These deltas are column vectors. Well, once we know the field, now we need to calculate the mode coefficients of the source. Because remember, our scattering matrices are relating mode coefficients from layer to layer, not the fields directly. So we calculate the mode coefficients by backward dividing the eigenvectors in the reflection region. The reflection region and source region are the same thing. Backward divide the eigenvectors with the source field we just calculated. So now we know the mode coefficients of the source. From there, we go to the global scattering matrix that we calculated, and we can calculate the mode coefficients of the reflected fields and the mode coefficients of the transmitted fields. Given that, we can convert those into actual field values by multiplying those mode coefficients by the eigenvectors. Remember, we have different eigenvectors for the reflection region and for the transmission region. And in fact, we may just want to jump straight to this. Calculate the fields immediately by combining all of this stuff, the eigenvectors, the S parameter, and the mode coefficients of the source. But once we calculate these, we'll actually have to extract the x and y components of the reflected electric fields and then extract the x and y components of the transmitted electric fields. So we'll store these in all separate parameters. Well, we only have the tangential components right now. We can calculate the longitudinal components using these two equations, which, if you remember, are derived from the divergence equation. So now we have all three field components on both reflected and transmitted sides. We're all ready to calculate diffraction efficiencies. So that's the next step. And we'll first calculate the magnitudes of the spatial harmonics, and then we'll use that to calculate the diffraction efficiencies of all of the reflected spatial harmonics. So this will come out being a column vector containing all the diffraction efficiencies. If we add all of those up, we get the total reflectance. And we do the same thing on the transmitted side. We'll calculate the amplitudes. We'll use this equation to calculate the diffraction efficiencies of the transmitted modes. We'll add all those elements up of this column vector and get total transmittance. So now we have total reflectance and total transmittance, in addition to the diffraction efficiencies of all the different modes, if we want that information. And the final last step is to add reflectance and transmittance together and make sure we get all of our energy back. So even if your device is going to have loss or gain, I would recommend setting that to 0 initially, keeping the real parts of your mu's and epsilons the same, but turning off the loss or gain, running your simulation, make sure you get conservation of energy, because if you don't, you know something's wrong. Then you can turn the loss or gain on and get your final answer. So that's it. That's the entire algorithm for rigorous coupled wave analysis. And hopefully you'll see that this is almost exactly the same as the transfer matrix method. The biggest difference now is that the matrices are larger, because now we have a whole set of spatial harmonics. It's not just one plane wave bouncing around amongst a bunch of different layers. It's a whole set of spatial harmonics that are now bouncing around amongst all these different layers. But at a high level, the equations are the same. The algorithm's the same.